behavior in the general parabolic nonlinear equations and its application to elliptic eigenvalue problems.
Thank you for introduction, and I also thank organizers for giving me a chance to talk here. I'm going to talk about asymptotic behavior in some parabolic nonlinear equations and its application to elliptic eigenvalue problems. This is joint work with my advisor, Professor Lee. Let's consider the following nonlinear elliptic eigenvalue problem. That is, Laplace phi is minus mu times phi to the p in the omega, and phi is 0 on the boundary of omega, and positive in the domain of omega, where omega is smooth and bounded in the whole space, and the exponent p is positive. We are interested in the geometry of the positive eigenfunction phi when the domain has some geometric property. More precisely, let's say the domain omega is strictly convex. Then here is our question. Are the level sets of the positive eigenfunction convex? We have the positive answer to this question for Laplace operator. Log of phi and log of phi for p equal to 1 and phi to the some power for p between 0 and 1 are strictly concave. These have been studied by many authors as follows. So now we are going to generalize the previous result to the fully nonlinear operator f here. So let me state some assumptions on operator. The first assumption is uniform ellipticity. We say the operator is uniformly elliptic when there exists two ellipticity constants such that for any symmetric matrix M and positive N, these inequalities hold. This will imply that the operator f is strictly increasing and Lipschitz continuous. If a uniformly elliptic operator f is differentiable, then the first derivative is an elliptic matrix. There is Pucci's extremal operators, which are the extremal case of uniformly elliptic operators. For symmetric matrix M plus is defined as the sum of eigenvalues with different weight according to their sign. For M plus, we put small lambda on negative eigenvalues and large lambda on positive eigenvalues. And we define M minus in opposite way, like this. And then you can check easily that these inequalities, that is, Pucci operators are supremum or infimum of some linear operators. Second, we assume that the operator f is positively homogeneous over the 1, like this. If a positively homogeneous operator is differentiable, then the f should be linear. So under these two conditions on operator, we have existence and uniqueness of nonlinear eigenvalue problem. For p equal to 1, Ish and Yoshimura proved that there is a positive eigenfunction phi in the viscosity sense, and the eigenvalue mu is unique and simple. So we deduce that the positive eigenfunction is unique up to a constant multiple. For p between 0 and 1, for any eigenvalue mu, you can find unique positive eigenfunction phi by using Perron's method. So to study the elliptic problem, let me introduce nonlinear parabolic equations That is for positive m, f of d squared u to the m is time derivative of u in a parabolic cylinder. We have zero boundary data and non-negative initial data. In particular, the operator f is Laplacian. It is well-known heat equation for m equal to 1, and porous medium equation for m bigger than 1, and fast diffusion equation for m between 0 and 1 respectively. Indeed, we are going to see that the positive eigenfunction phi can be approximated by normalized function of the solution u as time goes to infinity. And the exponent m is 1 over p. So let me state first our main result for m equal to 1. The theorem says, suppose that f satisfies ellipticity and positive homogeneity and concavity, and the domain is convex. If log of u is initially concave, then log concavity is preserved for all time. For elliptic problem, under the same conditions on operator and the domain, log of positive eigenfunction is concave. Let's see some remarks here. The Pucci operator m minus is a non-trivial example of concave operator satisfying ellipticity and positive homogeneity. And the concavity of the operator is required mainly when we study geometric property of elliptic and parabolic solutions. For m bigger than 1, we have a similar result. So under the same conditions on operator and the domain, and let's put an additional condition on initial data like this. And if the initial data to the some power is concave, then that concavity is preserved for all time. Again, for elliptic problem, eigenfunction to the some power is concave. We expect the additional condition on initial data is removable. So we'll discuss it later. So to prove the result, we'll take parabolic approach. First, we are going to find exact decay rate and show the convergence to the positive eigenfunction phi after suitable normalization of the parabolic flow as time goes to infinity. E to the mu t times u and p to the 1 over m minus 1 times u will turn out the right normalization of parabolic solution. Second, we'll show some geometric quantity will be preserved in the flow. To obtain it, we'll use the idea of Lee and Vasquez. They consider Laplacian. At the end, we get the geometric property for elliptic problem at the limit as time goes to infinity. So let's look at the uniformly parabolic equation first. That is f of d squared u is time derivative of u in a cylindrical domain. We first observed that the separable solution phi x times e to the minus mu t is a similarity solution of parabolic equation, where the constant mu is the principal eigenvalue corresponding to the operator f, and phi is the positive eigenfunction. Now let's define the function v by e to the mu t times u. Then the scaled function v solves the following equation. If you show that the scaled function v converges some function as time goes to infinity, then the limit function will be an eigenfunction. Here. So we have uniform convergence lemma as follows. Let operator satisfy ellipticity and positive homogeneity, then scaled function v converges to eigenfunction uniformly in the omega as time goes to infinity. The proof is the following. First, we observed that there is time t sub naught such that the parabolic solution has non-trivial bounded gradient on the boundary of omega from regularity theory. Then, by using Hopf lemma for eigenfunction phi, we get this inequality at time t sub naught. And by comparison principle, we get this long time asymptotic. So you can see here the parabolic solution decays exponentially. Then the scaled function v, defined as exponential e to the mu t times u of xt, is bounded. So the V-Carnot inequality for v will give uniform Holder estimate for scaled function v. So from Arzellas-Curry theorem, you can consider sequential limits of v. Let's define the set A as the set of all sequential limit of v, and constant gamma star as the infimum of constant gamma satisfying this property. So we get this bound for gamma star from these inequalities. Finally, you can show that the set A has only one element, gamma star times phi, by using maximum principle and regularity theory. Therefore, any sequential limit of V is gamma star times phi, so you get the convergence. Now let's go to the second part of the parabolic method. Suppose that the operator f satisfies ellipticity and positive homogeneity and concavity, and the domain is strictly convex. If log of u is concave initially, then log concavity is preserved. That is, Hessian of log of u is non-positive. To prove it, we approximate the operator f by smooth concave operator f epsilon, satisfying ellipticity and f2 prime condition instead of positive homogeneity. F2 prime condition means that f epsilon is close to a linear operator at each point. We can make this regularization by using the convolution with standard modifier. And we assume the initial data is smooth and strictly low concave. And let u epsilon be the solution with the operator f epsilon. Then let's set g epsilon to be log of u epsilon. Then g epsilon solves the following equation. You can see e to the g and e to the minus g and e to the g here, because f epsilon is not positively homogeneous anymore. So we're going to see the concavity of g epsilon. So for small delta, let's define the function z as the sum of primum of all second derivatives plus small error function psi, where a small error function psi will solve some ODE. And let's assume that there is a time t sub naught such that the function z is 0 at time t sub naught. The primum of second derivatives is achieved at the point x sub naught and with direction alpha. Then we note that the function z is negative at time 0 because initial data is strictly low concave and psi is 0 at time 0. So the first time t sub naught is positive. And we have the following boundary estimate. The second derivative of g epsilon goes minus infinity on the boundary of omega. In fact, when alpha, direction alpha is normal to the boundary of omega, then the second term, normal derivative is not 0 from Hopf lemma on the boundary of omega. And the first term, u is 0 from zero boundary data. So the first term vanishes for normal vectors. So second derivative of g epsilon goes infinity as x goes to boundary of omega. And when the direction alpha is tangential to the boundary of omega, in this case the second term is 0, since the tangential derivative is 0 on the boundary. And for the first term, the strictly convexity of omega will imply that the tangent second derivative is negative on the boundary of omega. So as x goes to the boundary of omega, u goes to 0. So the first term goes minus infinity. From this boundary estimate, we deduce that the maximum point x sub naught of all second derivatives should be an interior point. So we're going to look at the linearized equation for g sub alpha alpha. Time derivative of g sub alpha alpha has 3 terms. The last term having the second derivative of the operator is going to be non-positive from the concavity of operator f epsilon. And the second term, red one, is going to be very small from f2 prime condition. So we get this equation, inequality. And at the maximum point, we have gradient is 0 and Hessian is non-positive. So the first one is going to be non-positive from ellipticity of the operator, and these two disappear from 0 gradient. And we may assume that the mixed derivative with direction alpha is 0 at the maximum point by using a certain coordinate system that has alpha as one of x's, because direction alpha gives the supremum of all second derivatives, and hence the direction alpha is an eigenvector of Hessian of g to the epsilon at the maximum point. So we get simpler inequality here at the maximum point. On the other hand, t sub naught is the first time for z to be 0, so derivative is non-negative at time t sub naught. If you replace g sub alpha alpha by using the above inequality, you get an ODE for psi. But if you set the function psi to be minus delta times tangent function, then this will be negative for very small epsilon, which is contradiction to this inequality. Therefore, there is no time for z to be 0. That is, second derivative of log of u to the epsilon is going to be very small for very small epsilon. Therefore, letting epsilon and delta go to 0, we conclude the log concavity of u. Now we have the following corollary for elliptic problem. Under the same conditions on operator and the domain, eigenfunction phi is log concave. To prove it, let's take the distance function as the initial data. Note that if domain is convex, then distance function to the boundary of omega is concave and also log concave. So from the previous lemma, the parabolic solution is log concave for any time, namely the second difference of log of u is non-positive for any x, y, and time t. Therefore, the uniform convergence to positive eigenfunction as time goes to infinity will preserve the sign of the second difference. So this completes the proof. Okay. Next part is about the general parabolic equation with the exponent m bigger than 1. That is, f of the squared due to the m is time derivative in a parabolic cylinder. This parabolic equation is degenerate when u vanishes because the diffusion coefficient is m times u to the m minus 1. And the degenerate parabolic equations arise in the study of gas flow in a porous medium and underground water infiltration. Here, the solution u means density, and the function v, defined by u to the m minus 1, is pressure. There are several properties for porous medium type equations. One of them is scaling property. Let's say u is a solution, then the scaled function u tilde, defined by a times u of bx, ct, is also a solution when this relation is true. And we have special solution called Parabolic solutions taking the following form, which are source type solutions for porous medium type equations. You can compare it to Gaussian function for heat equations. From Parabolic solutions, you can expect waiting time phenomena, free boundary problem, and so on. So to avoid them, we are going to consider the initial data u sub naught having non-trivial bounded gradient on the boundary of omega. Let's look at the asymptotics of degenerate parabolic equations. First, we have Aronson-Vanillan inequality for the operator elliptic and concave operators, like this. It can be proven by using maximum principle for porous medium type equation and the concavity of the operator. And we have the following uniform convergence. Let the operator satisfy ellipticity and positive homogeneity. Then the scaled function u to the 1 over m minus 1 times u goes converges to eigenfunction to the 1 over m as time goes to infinity. We can prove it by comparison with the separate function capital U, which is a similarity solution of porous medium type equation. Now we are going to show square root concavity of the pressure. So to prove it, let's approximate the equation as follows. We add small eta on the boundary and initial data. Then for each eta, the equation for g sub eta, which is defined by u sub eta to the power m, becomes uniformly parabolic for each eta. And let's denote u to the m by G, and u to the n minus 1 over 2 by W, which will be our geometric quantity. Since we have uniform Lipschitz estimate with respect to eta, it is sufficient to show concavity of W sub eta for each eta. We have the boundary estimate. Let the operator satisfy ellipticity and positive homogeneity in concavity, and let domain be strictly convex. And let's put an additional assumption on initial data like this. Then for small eta, the second derivative of W sub eta will be very negative on the boundary of omega. The proof is similar to the uniformly parabolic case, but we need uniform bound for second derivative. So to get this, we put an assumption, extra assumption on initial data. So this will imply the ratio of time derivative and the solution U is bounded. So we can use this bound to control the second derivative of U from the equation. In general, we need to prove a weighted C2 gamma estimate up to the boundary. So, suppose that operator satisfies ellipticity, positive homogeneity, and concavity, and domain is strictly convex. And let's assume the previous boundary estimate holds. If e to the n minus 1 over 2 is concave initially, then the concavity is preserved. The proof is the following. First, we fix eta, and let's approximate the operator f by f epsilon, which is smooth and concave, and satisfying ellipticity and F2 prime condition as we did in the uniformly parabolic case. And then the geometric quantity W epsilon satisfy the following equation. You can see W to the n minus 3 over n minus 1 and W to the minus sign of that. So we are going to look at the concavity of W epsilon. So we are considering the second derivative plus and small error function psi. The previous argument for uniformly parabolic case is also applicable to this general parabolic equation, except some modification like tilted, perturbed second derivative, which will help the third derivatives cancel out in the equation, and the small error function which will solve another ODE. So since the remaining part is similar, so let me skip the rest of the proof. So lastly, we have the following corollary for elliptic problem. Under the same conditions on operator and the domain, eigenfunction to the 1 minus p over 2 is concave. So I'll stop here. Thank you.